Hello, everyone, and welcome to our live session for today, which is November 4th, 2025. My name is Matthew. I work on the behind the scenes pieces. I'm also one of the um, instructors for our online classes, and we are excited to be here with you today. So I'm going to do a quick introduction, then we will get to questions. So the way this works is please post your questions on in the chat, and we see all the questions. We generally try to pick questions in the order that they're asked, but we do jump around to make sure more people get the chance to have their questions addressed. We also try to pick from a variety of topics, and we try to keep things at the level of general level that everyone can understand. And please ask your questions only once. We see all the questions, so spamming the channel with question after question is less likely to get your question picked than more. If you want to email your questions, you can scroll to the top of the chat and use the email address there. Please like and subscribe and click on that bell icon to follow us on YouTube. That way you'll know about upcoming live sessions. And we have a mailing list. If you'd like to join our Google listserv, you can do that. There's also a calendar link so you can find out about upcoming live sessions. And for those of you who have found us through YouTube, welcome. For those of you who don't know that we have classes, we have Coursera courses, which we offer for free. We currently have 3 astronomy, astrobiology, history and philosophy of astronomy courses. And we hope that you'll go check those out. Now, Chris, I'm going to hand this over to you. The way you usually like to run this is that we will, have a topic for discussion that will hopefully stimulate some comments and questions, and then we'll go from there.
Okay, welcome everyone. We're starting a little late, so I'll jump right in, and I have to finish slightly early because of another engagement. So my topic this morning is interstellar comets. One of them has been in the news lately, 3I/Atlas. The designation pretty much tells the story. It's the 3rd interstellar comet to be identified. The first was Oumuamua. That's 1I, Oumuamua, and the second is a Borisov, a comet called Borisov, 2I Borisov, actually found first of the 3. And these are extremely interesting objects, proving that objects can travel between solar systems, because these are objects from another star system, comets that got unbound from their star systems and traveled through interstellar space to reach our solar system. They're moving at a high enough speed that they have hyperbolic trajectories through the solar system, and they only spend a short time here and then leave forever. So observations of them are tricky because you have to be on it right away, and you only maybe have a few weeks to observe them. Atlas was picked up pretty early, and it's been confusing and intriguing people because it brightened substantially before it reached its closest approach to the sun, which was about 1.8 AU, or almost 2 times the Earth's sun distance. And it has generated some controversy in the hands of Avi Loeb, who's I would say a bit of an iconoclast in the astronomy community. He went all in on Oumuamua as an interstellar, as an alien artifact rather than an interstellar natural occurring body, writing a book about it, giving endless interviews, sort of hogging media attention. He essentially is wrong. The planetary science community has explained Oumuamua and these 3 objects in conventional terms. There's no reason to reach for the radical hypothesis that they're alien artifacts. So let's just ignore that for a minute and notice that these are interesting objects coming from other star systems. And so astronomers home in on these objects, this handful that are known, to learn as much about them as they can before they disappear forever.
All right, thank you very much, Chris. So that gives us some interesting stuff for people to think about and ask some questions about. So if you have questions about this object, please post those in the chat. So the first question that we have for today is from Pecornin, who would like to know, What do you think the great filter is when it comes to life in the universe? Is it still ahead of us for our civilization?
So the idea of the great filter, it's a concept in astrobiology. It dates to a philosopher actually called Robin Hanson. I think it's over 20 years ago he wrote a paper about this. It's gone into circulation now. It's partly an explanation for the Fermi question, where are they? The idea that there are so many potential sites for life in the galaxy and beyond that it's slightly puzzling that so few of them seem to have reached a stage of technology and space travel and made themselves known to us. Astronomers do not believe we've made contact with alien civilizations, UFO reports notwithstanding. So the great filter is one of the explanations for why this might be the case. And it essentially says that in the progression from the rudiments of life, the very first life on a terrestrial planet, to a stage of technology and civilization and intelligence, there may be one or more hard steps, that is, transitions or evolutionary progressions that are difficult or just happen with low probability. And essentially they act as filters. So very few planets with microbial life, for example, may pass through the filter or the hard step of going to multicellular life. It took a couple billion years on the Earth, so it obviously didn't happen very quickly. Another hard step may be the one that develops intelligence or brains. And brains have an advantage, of course, an adaptive advantage within natural selection, but they also incur a huge energy cost, and they are extremely fragile parts of an organism. So there are downsides to having a brain as well as upsides. Perhaps the most obvious great filter would be the technology filter, where perhaps instability in global technology, leading to nuclear weapons or pandemics or things that could wipe out a civilization, mean that that's the great filter. And so many species become evolved or even gain intelligence, but never pass through the filter of getting stable, long-lived technology. So the great filter is just an idea. It's a potential explanation for the absence of contact with intelligent civilizations.
Excellent. The next question is from another one of our participants. Jane would like to know, what is your opinion of Avi Loeb?
Well, I'll speak cautiously. I know him not incredibly well, but fairly well as a colleague. He's an inestimable cosmologist. His training is cosmology. He's a theorist. He's the head of the department at Harvard. He's written hundreds of research papers and technical articles of all kinds. And he's highly respected in the cosmology community. My opinion of him just took a notch down because one of the premises of being a scientist is you stay in your lane. In other words, you speak to your own expertise. You talk about things you know and can understand. I have no more insight into the fundamental drivers of climate change than any other physicist or astronomer. You need to talk to someone who's an expert in climate change. And although cosmology and planetary science might seem to be part of the same subject, astronomy, they're very different disciplines. Planetary science is all about rocky objects and it's geological stuff as well as astronomy. And cosmology is about the size, shape, and contents of the universe, quite a different discipline. So when Loeb went out of his lane from cosmology to planetary science, he was no more qualified to speak about these matters than anyone else, any other smart person not trained in planetary science. And I think he made some mistakes. Unfortunately, due to some nature of his personality, when the planetary science community sort of gathered together and by consensus realized that they could explain Oumuamua naturally as an astronomical phenomena, he just doubled down and tripled down, and he has not let go of his position. And at that point, I think he squandered some of his scientific credentials with the larger community.
The next question is from one of our live participants who would like to know, how quickly could we act if an object from outer space were on a collision course with Earth?
I think we would have plenty of time. So the classic doomsday scenario of a Hollywood movie would be that an object is found that's heading towards the Earth and could cause a global catastrophe or a mass extinction. And then we'd have hours and suddenly there's a clock running in the corner and the second hand's ticking down. That's not the way it will work in practice. We have sufficient monitoring of the skies with small and medium-sized telescopes that are essentially scanning the whole sky for moving objects and near-Earth objects that we would pick up an incoming object months and actually years before it would possibly arrive here. So our surveillance is really good. And we've picked up most of the objects more than about 200 meters in diameter. Now, objects smaller than that, 100 meters, can cause, regional devastation on the Earth, so we don't have a complete inventory of all the threatening objects. But if they come close enough to be picked up by our telescopes, we're still going to have quite a lot of time to act. And the way we could act is twofold. We could send a spacecraft out to the location of that object, travel alongside it, just essentially join it in its path, and use the spacecraft as a gravity tractor to slightly deflect its path away from the Earth. Another possibility, of course, is to the more violent possibility of blowing it up, but that's not a smart idea because the momentum of all the pieces would be directed in the same way towards the Earth. A more clever approach, of course, would be to attach an explosive to the object or perhaps detonate a bomb to one side of it to kick it off to the side and give it a different trajectory. These are all untested hypotheses and mechanisms, but we could put them into play if we needed to.
The next question from one of our live participants is, sorry, let me get this in here. That they are, Yazan says, I'm curious about Avi Loeb's recent claims that this new comet is accelerating in a way we can't explain with gravity alone. Do you have any thoughts on what might be causing that?
So non-gravitational acceleration was one of the arguments Loeb made about Oumuamua being an interstellar, an artifact of an alien civilization rather than a naturally occurring object. It's a tricky claim to make, and I'm just going to withhold judgment because the truth is that the experts have not weighed in yet, and the object is being observed and the data has not all been produced. But the interaction of the object with the solar radiation, which exerts a pressure force, radiation pressure, depends a lot on the composition of the comet. Obviously, if it's highly reflective, the force imputed onto the comet is larger and the reaction is larger. So you need to know what the comet's made of. You need to know its size pretty well to understand how the solar pressure will affect it. It's not simply a matter of its velocity and trajectory. So I would just say there's not enough information to draw the conclusion that non-gravitational forces are at work.
Excellent, thank you. All right, switching topics a little bit here. Connor Alp asks, if given the opportunity, could we easily locate a second planet similar to Earth?
We will be locating such planets. We have located fairly Earth-like planets, if not exact Earth clones, that are planets that are within like 5% or 10% of the mass and size of the Earth and are in the habitable zones of their stars. The nearest of these planets is dozens of light years away. In other words, not among the closest exoplanets. The best bet for an Earth-like planet very close would be in the Proxima Centauri system, but the evidence is a little mixed there on what the nature of the planets in that system are. And they're not classical Earths in classical Earth-like trajectories or orbits. So we have found nearby Earths. They're not very nearby, and they're certainly not nearby enough to represent a planet B in case we mess up the Earth so badly we have to leave, because we have not, of course, traveled any further. Humans have not traveled further than the moon in the 60 or 70 years of the space program. And that's a tiny fraction of the size of the solar system. And then you've got a factor of 1,000 more distance to get just to the nearest star. So the prospects of interstellar travel are exceedingly remote. And so an Earth-like planet a few dozen light years away is only of conceptual or hypothetical interest.
The next question is from Terrence, who's on with us live, who would like to know what is the best, I'll make this more general. The specific question is what's the best vegetable to grow on Mars? But generally, what are the best plants to grow on Mars, like potatoes or carrots, because of the radiation from the surface? Is it possible to bioengineer new plants to grow on the surface?
So the premise of The Martian, the book by Andy Weir, and then the film that became quite famous and was an excellent film, is of course that the stranded Martian sustains himself by growing potatoes, essentially using the Martian soil and his own excrement. That's not plausible. The Martian soil is too poor, even enriched by manure, to grow potatoes. So potatoes are not a viable crop. That was one of the areas in which Andy Weir sort of pushed the envelope of truth a bit, but it made for a good story. On terrestrial experiments on Mars-like conditions and Mars-like soils, and a variety of vegetables have been attempted to grow. Potatoes do quite well, but they don't do, that's with suitable nutrients added, but they don't do as well as some other vegetables. Carrots do extremely well, and they perhaps do the best of all. So there's perhaps a dozen different vegetables that have been attempted to grow in Martian soils, and most of them don't fare very well because the soil is just too poor. Essentially, it's high in perchlorate in most regions, and that's a very toxic material that has to be buffered to be able to grow normal crops. If you want to feed people on Mars, the best bet actually is algae and insects. Insects are very cheap to grow, very easy to grow and feed. And algae is also very easy to grow in aquaculture, and it has high nutritional value. So the truth is that the Martians, the first Martians that we send there and that live there, will probably not be eating many vegetables, and they certainly won't be eating animals. They will probably be eating high protein, high nutrient sources, in particular algae.
The next question is from one of our live participants. Adrian asks, is an atom a perpetual machine? What keeps subatomic particles in constant motion?
That's an interesting question. We can think of an atom as a little machine. I mean, it has mechanical properties. It has energy states. It has vibrations. And in that sense, it is eternal, because if you have a single hydrogen atom in space, it will have its frequencies of oscillation. It will have its fundamental modes of interacting with light. And those modes will not change over cosmic time. So in that sense, atoms are eternal. Now, it's an open question in physics whether normal atoms are stable, because grand unified theories suspect that normal matter must be unstable for grand unified theories to work. But we've never seen protons decay, and the experiments to look for that have been going on for almost 20 years now. So proton decay lifetime, if it exists at all, is more than about 10 to the 35 years, which is essentially forever. So atoms as little machines, yes, they are machines, with one major exception, of course. Machine conjures up the world of Newtonian physics, and atoms, of course, are described by quantum physics, which is governed fundamentally by probability. So it doesn't have the mechanistic, deterministic nature of the word machine. It's a little different because of the quantum aspect.
The next question is from AB, who asks, does the fabric of space-time, or anything for that matter, survive in the theoretical Big Rip scenario at the end of the universe?
Well, the Big Rip, if it happens, which is this sort of a crescendo of accelerating space-time, which essentially pulls apart all physical objects and eventually even pulls apart atoms themselves. It is the crescendo of the structure of space-time itself. So you could think of it as space-time pulling itself apart, but more significantly, it represents the end of all the structures in the universe, which will be pulled apart by endlessly accelerating space-time.
The next question is from Lawrence, who's on with us live, and asks, is dark energy a quantum field, i.e., is it subject to quantum fluctuation?
Dark energy is of unknown physical nature. So that's the first most important thing to say, which is to say we don't understand it fundamentally. We don't have a theory of it that we can test. So everything is within that context. But yes, it is going to be a quantum entity because it emerges from the vacuum of space. And we know that the vacuum of space can create, has latent energy to create particle-antiparticle pairs virtually that come in and out of existence all the time. That's been demonstrated in the lab. So at some level, whatever dark energy is, it must have a quantum aspect. The nature of the quantum field, however, is very uncertain because we have no kind of quantum field known to physics which has negative pressure, which is a property that dark energy must have to cause space-time to expand forever.
The next question is from Hernan Reyes, who sent an email. You mentioned recently that the last supernova in our galaxy was 400 years ago, and that one is overdue. The question that is, which supergiant stars are in our neighborhood and near enough to cause significant problems or even heavy damage to us here on Earth?
Well, the stars that people have had their eye on, and they're well known because they're naked eye objects to astronomers for centuries, are Betelgeuse and Antares. Those are red supergiants, and they are stars massive enough and fairly far along in their lives that they will die as supernovae. That's beyond doubt. What is uncertain, however, is what stage of their life they're at. We can inspect them and observe them and understand that they're in the later stages of the fusion chain that ends with iron, which is the end of the road. And then when eventually all the silicon has been turned into iron, pressure support in the core is lost and there's core collapse, and then the jettisoning of a supernova envelope. So we don't know how close those two stars are to that episode. These stars are also hundreds of light years away. And so even when that happens, should it happen in our lifetime, it will not really affect the Earth dramatically. These will be visible in the daytime sky. They'll be spectacular objects, visible in the daytime sky easily, not rivaling the sun, but certainly far exceeding Venus, for example, in brightness. But they're far enough away that their radiation in the blast wave will have mild effects on the Earth, perhaps a slight increase in the mutation rate, but nothing dramatic.
The next question is from David Gold, who's on with us live. What is the major roadblock to unifying general relativity and quantum field theory?
The major roadblock is, you could understand it at a conceptual level, you don't even have to go to the physics, which is that quantum field theory deals with, as the term implies, quantized entities, which is energy that is discrete and quantized. And that's fundamental to quantum theory. Whereas general relativity is a smooth theory. It's a smooth theory of space-time, a geometric theory of space-time, where space-time is a mathematical manifold that can have curvature, could even have ruptures and disconnections, but it's fundamentally smooth. So these are very different conceptually. And of course, their theoretical basis is quite different. So people are going to have to reach for a very different type of theory to merge quantum and general relativity.
Excellent. Thank you very much. The next question is from Dennis, who asks, what is your view on the research out of Canada that suggests dark energy does not, in fact, exist and the universe's expansion is or can be explained by changing physics?
Well, it's an interesting idea. There's a group in Canada. There's several groups that are working on this idea. So given that we don't know what dark energy is, and its discovery really now is 30 years ago, 1995, 96, the accelerating expansion of the universe was discovered 30 years ago, and the imputation of dark energy goes back that far, and we really haven't made a lot of fundamental progress. So people are reaching for other ideas. If you choose to view the constants of physics or the fundamental properties of physics not to be unchanging over cosmic time, which is the default assumption of cosmology, then indeed you can change the forces or the constants of physics such that they would mimic something like an expansion of the universe. So it is true that if you open the box on changing the laws of physics, the rules and the constants that we view as constant, then you can do away with the idea of dark energy. It's a fairly radical hypothesis, however, because you would need direct evidence from observation that those constants of nature or forces of nature do change over time or with location in the universe, and we have no such evidence.
The next question is from Jane, who's on with us live. I'm interested in your opinion on the odds or likelihood that at this moment in the history of the universe, 13.8 billion years after the Big Bang, of humans being alone in the universe.
Well, it is conceivable and it's possible. We do not get to argue from our privileged location or our privileged situation as intelligent observers of the universe, what the general case is or what the universe may or may not have produced. All we know is that the ingredients for life are abundant throughout the universe. There's been plenty of time, including 8 billion years before the Earth formed, for biology to evolve into complex organisms on trillions, literally trillions of habitable planets, potentially habitable planets. And so it becomes unlikely a priori that we are not alone in the universe. It would be very unlikely for us to be the only biological entities. But logically, it is possible. If life on Earth was a fluke somehow, the combination of chemicals to form the first cell was just extremely unlikely, as a few people have argued, then it is possible we're alone in the universe. But I would say most astronomers do not hold that position.
The next question is from, excuse me, is from one of our live participants who would like to know, let's say that you had been chosen to lead an international collaboration to learn the secret of dark energy. How would you organize such a project and what goals would you hope for?
Well, it doesn't have to be a hypothetical involving me because that project is being done. I'm not involved in it. I'm sort of, I would say, in the twilight of my research career, so I'm not as active in cosmology as I used to be. But the Vera Rubin telescope, for example, which is commissioned and taking fabulous data and is going to survey the entire sky from the southern hemisphere and look at variations in the sky and make exquisite maps of the sky. One of its prime objectives is to map out the properties of galaxies and clustering and lensing to diagnose dark energy and whether it's changing over time and with location in the universe. So that telescope's only just started doing its work. And if I were designing a project to learn more about dark energy, that's a pretty good project to design. That's not why it was designed. It was designed even before dark energy had been discovered. But it's the perfect tool for learning more about dark energy.
The next question is from one of our participants sent an email asking, could relatively small blue supergiant stars like Rigel cause damage if they were somehow to go supernova close to us?
So there's two parts of the question. The question about whether blue supergiants can go supernova, and the answer is yes. There are red supergiants and blue supergiants, and the color there does not really tell you much about the interior of the star, which is at incredibly high temperatures when fusing heavy elements into even heavier elements. It's the outer envelope of the star, whether the outer envelope of the star is cool, perhaps 3,000 to 5,000 Kelvin, or hot, 10,000 to 20,000 Kelvin. The mass of the star is what determines its fate. And so for a star that's born with more than about 8 times the mass of the sun, whether it becomes a red or a blue supergiant, it will die as a supernova. So yes, blue supergiants can go supernova. The question of whether there's one near enough to the Earth to cause damage and be of interest, Rigel being one example, that's in the Orion Nebula or in the Orion constellation. The answer is no. There's no blue supergiant close enough to do damage. The boundary for doing damage to the Earth for supernova is roughly 30 light years. Incidentally, the fact that we know blue supergiants can go supernova comes from supernova 1987A in the Large Magellanic Clouds. That the precursor star was observed and it was a blue supergiant. So we know that blue supergiants can go supernova. The 1987A supernova, of course, was very far away. It wasn't even in our galaxy. There are no blue supergiants within 30 light years, and so there's no likely supergiant going to cause damage to the Earth by dying as a supernova.
The next question is from one of our live participants. Is there still any talk about the New Horizons mission? Will they try to observe any more objects in the Kuiper Belt?
New Horizons is a live mission, of course. It's the 5th man-made object to leave the solar system after the 2 Pioneer spacecraft from the 1970s and the 2 Voyager spacecraft left the solar system decades ago. So New Horizons whizzed past Pluto and it's headed through the Kuiper Belt. It's still taking data. It's not on a trajectory that will take it very close to any notable sized object, but the cameras are working. At that distance, of course, the light travel time or the signal travel time is getting on for a good part of a day. So it takes a while to get the data back. But it is on the lookout for interesting objects, and I think the scientists involved are just monitoring its data stream routinely.
The next question, it's related to an earlier one, but it's, I think, enough different that we can cover this as well. Arif Roni asks, what are your thoughts on this quote from Yana Levin saying, "We now think gravity is probably not a fundamental force, um, that it emerges from quantum mechanics."
Right. Jan Levin is a well-known astronomer and writer and educator and popularizer of science. I know her quite well. That's a speculation. We don't really know how to explain gravity in any other way than general relativity. General relativity is a self-contained theory of curved space-time where mass and energy cause the curvature of space and time, and objects move according to the curvature of that space-time. It does not refer to or make any reference to quantum physics. So if you wanted to somehow take quantum physics, our foundational theory of the very small, and make gravity emerge from that, you have to somehow find a way of bridging the enormous range and force strength. So gravity is dozens of orders of magnitude weaker than the strong nuclear force that holds the atom together. So that's a great challenge in any theory that seeks to explain gravity as an outcome of quantum theory, because gravity is so incredibly weak. And that has been a challenge that theorists have struggled with for decades.
The next question is from Wendy, who sent an email. I read that the sun merged 2.5 billion years ago with another star, um, that potentially caused, or led to the conditions for life. What are your thoughts on some idea like this? How would we even be able to tell if our sun merged with another star?
I don't think there's any evidence that the sun has had any interaction or merger in the time since the Earth has been around. So the age of the Earth is the same essentially as the age of the sun and the solar system. And we have a pretty good indirect evidence of the dynamics of the solar system from its formation through the orbits of the planet, through chronographic measurements of the age of rocks and interstellar debris. So there's no indication in any of that data that the sun had an interaction or merger with another star. Now, at the time the sun probably formed as one of a series of stars from a nebula that had more than enough mass to make one star. And so it's possible that very early in the sun's life, really early in the sun's life, it had neighbors and had interactions with those neighbors. But if that happened, that would be before 4.5 billion years ago.
The next question is from one of our live participants, who asks, does Oumuamua's trajectory follow a classic, it says three-body problem, but I assume they mean, does it follow a classic gravitational trajectory through the solar system?
There was a debate in the literature as Oumuamua was observed about whether it had non-gravitational forces operating on it. And that was the crux of the controversy that led Avi Loeb and a few others to hypothesize that maybe it was an alien artifact, that normal gravitational forces on an interstellar comet could not explain what its trajectory was. It was a hyperbolic trajectory passing through the solar system and then disappearing from view or observation. But calculating those forces depends a lot on knowing the composition of the comet and its reflectivity, and therefore what the forces operating on it were from the sun. And there was a debate about that. I think the way the dust is settled, given that we can't observe it anymore, is that there's no compelling reason to believe non-gravitational forces were operating.
The next question is from an email. What's the current thinking on Jupiter's development in the protoplanetary nebula, How did it separate the terrestrial planets from the outer planets? And did this development clear a path for life to develop on Earth?
Well, there have been simulations, very interesting simulations, that suggest very strongly that the planets were not always in the positions they occupy now, that planet migration was a feature of the early solar system. As we know, it must be in other solar systems because we see hot Jupiters among exoplanets, and hot Jupiters could not have formed where we see them so close to a star. There's just not enough material to make a Jupiter that close to a star. So they must have migrated from further in. In the solar system, it's a complicated story which involves the migration of planets, not as dramatic as forming a hot Jupiter, and a couple of the outer planets changing their position over time. And so, the details of this, of course, are up for grabs and argument because you have to run a simulation and you have to trust the simulation. If you vary the initial conditions slightly, the simulation has a different outcome. But it's definitely true that Jupiter was not always in exactly Jupiter's position. And the migration of the planets in the early phase of the solar system sort of put a limitation on how fast the terrestrial planets could form because giant planets moving through an inner solar system disrupt the orbits or could even toss out a terrestrial planet. There's even an argument in several papers that argue quite compellingly or convincingly that the inner solar system had a fifth rocky planet beyond Mercury, Earth, Venus, and Mars, and that early planet was tossed by the motion of one of the large planets. So it's pretty crazy in the early solar system, these chaotic orbits and migration of planets and so on. And the stability we see around us, which does seem to be long-term stable, is a phenomenon of the last few billion years.
The next question from Rajendrani is, can you please recommend some books on astrobiology for beginners or enthusiasts?
Right. So there are some interesting books on astrobiology. There's a textbook that's used a lot in astrobiology courses around the country for teaching at the university level, but it's non-technical. It's beautifully illustrated. It's not cheap, by Bennett and Shostak. Life in the Universe, I think it's called. But if you look for those authors, Jeff Bennett and Seth Shostak, you'll find it. And you can find used copies on Amazon. That's a really good book because it summarizes the research. They put out new editions every few years because this is a fast-moving field. And that is the single book I'd recommend the most. Of course, if you want to learn about astrobiology, I would strongly recommend our MOOC on the subject, which we launched in 2019, I think. It's on Coursera alongside our normal astronomy course and our history and philosophy of astronomy course.
The next question is from one of our live participants who would like to know, is it possible for, or why do you think it hasn't, why do you think that comets and meteors striking the Earth have historically not affected the mass of the Earth, or have they?
No, they haven't. All interstellar objects are tiny fractions of the Earth's mass. If you think about it, if you want to think about it one way, if you swept up all the asteroids in the asteroid belt, and the biggest asteroid series is 1,000 kilometers across, if you swept all of those up together, it's only 4% of the mass of the Earth. So you can therefore easily see that a typical asteroid or comet, comets are even smaller than asteroids, 5 or 10 kilometers across, are an infinitesimally small fraction of the mass of the Earth. So even the deposition of this material over centuries, millennia, and eons has not significantly changed the mass of the Earth.
The next question is from one of our live participants who asks, can you talk about the Earth's rotation or the Earth's core? Is the Earth slowing down? Is it speeding up? How is the rotation of the Earth changing, and how does the core affect that?
So there's an interplay between several things. There's the interior physics of the Earth, which of course has a solid core and then a liquid core too. And that, in terms of angular momentum of a spinning planet, there's a viscous force and therefore a drag exerted between the core and the surrounding material. But the Earth is an entity to itself, and so its angular momentum would only change by interaction with another object. And that other object is the moon. So the moon is on a tidally locked orbit of the sun, which is why we always see one face. And the interaction between the moon and the Earth is actually slowing down the rotation of the Earth. And that conservation of energy and angular momentum means the moon is moving very slightly further away from the Earth every year. It's about 4 centimeters a year, I think, is the amount. It's been measured by reflectors left on the moon by Apollo. So take that, Apollo deniers. And the Earth is slowing down very slightly. And I think the increase in the length of the day is about 1/1000 of a second a year. So it's really small, negligible, but it's a real effect and we can measure it.
The next question is from Nicholas, who's on with us live and asks, I remember hearing that Mars gravity would affect human muscles negatively long term. So how long would a Mars mission last, and how would humans stay long term on Mars?
So the simple answer is we don't know what the effect of reduced gravity on human physiology would be. Our biggest experiments, of course, are from the International Space Station, which has been continuously occupied for 25 years now. And some astronauts, of course, have set longevity records of over a year. I think over 2 years is the record. And that's microgravity. It's not absolutely zero, but it's essentially weightless. And that has serious health effects. So we know that microgravity, or essentially zero gravity, has bad physiological consequences. Mars gravity will be 38% of Earth gravity, so just under 40%. And that's a significant fraction of Earth gravity. So the vascular system and the capillaries and all the other things that are dominated by gravitational effects on the Earth would still be present, but about half reduced. And that doesn't seem dramatic enough to infer serious health problems, but the simple answer is we don't know. It depends on the longevity. So for long duration Mars missions, and remember the minimal Mars mission for people who travel 8 or 9 months in a minimum energy trajectory to Mars, and then spend around 2 years on the surface for the next minimum energy return, and then come back for 9 months, they will have experienced 2 years of reduced gravity, 40%, and 18 months of zero gravity, getting there and back. And that almost certainly is going to have serious health consequences. As for longer term habitation of Mars, where people live and die on Mars and have children and there's a colony, we simply don't know. There's just not enough research been done to understand how half gravity or about that would affect human physiology.
The next question is related to that is, how do we answer such questions? Do we just find out when we first send people to Mars? Is there other research that we can do on gravity and how it affects humans here on Earth? Or is this something that we just find out long term by trying it?
I mean, I think the simple answer is we don't really know until we do the experiment. However, we can model it and we can do so it is the body's mechanisms, the way blood flows, the way capillaries operate, the way osmosis happens within the body, the transfer of nutrients between organs and through the bloodstream. We can model all these things. And so at the microscopic level, or at the level of the individual nutrients and fluids and solids in a body, we could model what the effect of reduced gravity is. And those models are probably fairly reliable. But they don't have the power to be able to predict a health outcome, because of course the human body is incredibly complex and all these systems work together. So the modeling of reduced gravity on individual organs, on individual vascular systems, on individual capillaries or whatever it might be, or the heart, does not tell you the totality of the story. And that's why in the end the modeling will not really truly answer the question.
The next question is from Sergey, who asks, why are there blue stars in old globular clusters?
That's an interesting question. And it seems to be the case that some old globular clusters have had star formation since their origin. The simplest idea of globular clusters is that they formed in the halos of elliptical galaxies along with the initial collapse of the galaxy. So they are primordial. They go back to the old galaxy population, and that would be true in the Milky Way too. The globular clusters in the Milky Way, in the halo of the Milky Way, formed when the halo formed, probably 11 billion years ago. And so most of the stars are consistent with that. A stellar population that ages for that length of time would have only surviving main sequence stars that were quite cool and red, because all more massive and bluer stars have evolved off the main sequence and died as white dwarfs. But we do see some blue stars in globular clusters, not all, but in some. And so it seems like there are intermediate age populations, that is 2 or 3 billion year old populations mixed in with the old stars. And there's a very active debate as to why this is. It doesn't happen in all globular clusters. It's only a handful or a small number of globular clusters that seem to be intermediate age, so they probably formed well after the host galaxy formed. Now, how did that happen? How did a gas cloud form a globular cluster so long after the initial huge galaxy cloud formed? We don't know. So it's an interesting little niche of astronomy to try and figure out the blue stars in globular clusters.
The next question is from one of our live participants. How do you feel, or what are your thoughts on the Neuralink that one of the companies owned by Elon Musk is developing?
Well, Neuralink is a Musk company that's doing what other companies are doing. Neuralink gets more publicity than the others, I think. And it's designed to use brain sensors and probes to diagnose what's happening in the brain and to speak to the brain and potentially do a very powerful thing, which is give people, who have limited interaction with their bodies or have suffered trauma, a way for their brain to communicate directly and control artificial limbs or to control a larynx if the larynx is non-functional. So it's a very powerful principle that you can use brain implants to functionally operate parts of a body that no longer function directly from the brain. The limits on this are strong, though. The first experiments, some have been failures for Neuralink, and they've had a few successes, limited successes. So this is a field very early. It's very much in its infancy. It'll be interesting to see how it develops, because for people who've suffered severe trauma or accidents, it could be a way of completely changing their lives. So I approve of the idea of the technology, but there are, of course, significant ethical issues associated with using it and developing it.
All right, we are getting close to needing to wrap up. We will take one final question for today, and that question comes from a live participant who asks, when the moon was formed, was it closer to the Earth than it is today?
Yes, the moon was substantially closer. In fact, you can do a visualization of the moon appearing 30% bigger in the sky than it does now, because that's about how it was soon after it formed. The moon, we think, formed from a catastrophic impact of a Mars-like object with the Earth, and that material splashed off the Earth mantle material, essentially, while it was still molten, coagulated into an object, circularized the orbit, and then the orbit gradually has shifted due to the interaction between the Earth and the moon, and that migration of the moon away from the Earth continues at a slower pace than it was originally, but still at a measurable level. So yes, the Earth-Moon interaction is quite interesting, and it speaks to a time when the moon was substantially closer to the Earth than it is now. That's a good question to finish with. We've covered everything: cosmology, comets, the moon, Neuralink. So quite good range of topics as always. I'm not sure when our next session is, but it'll be, Matthew can tell us, and I have a trip coming up, so maybe we have a slightly larger gap than usual.
Yeah,
but
that's correct.
We'll be with you probably in about a month, I think.
Yep, that is correct. The next session is Thursday, December 4th. So
Okay.
there's a little bit of a break, but we will be back with you in 4 weeks, everyone.
Okay.
Excellent. Well, thank you very much for joining us today. We appreciate your time. It's always great to see you and read your questions and gather them up. I'm sure that there will be exciting astronomical events between now and the next time we get together. So thank you all again, and take care.